All right, so welcome everyone. We are very happy to have with us Professor Antonia Wachter-Zeh from Technical University of Munich, which is one of the leading centers in Europe in our general field, and in particular information and coding theory and communications. And Antonia got her PhD about 10 years ago, is now associate professor at Munich. And she's got a number of awards, including some of the most prestigious European awards for funding her research. Some of you will remember Rawad Bitter, who is here listed as one of the co-authors, and also we have I think Sršt Kashana, who also after his graduation went to Antonia's group as their postdocs or visitors. And then without further ado, welcome Antonia. Her talk is on systematic function correcting codes.
Thank you, Mina, for the nice introduction. So, and thanks for the invitation to give this talk. So I'm happy to talk about systematic function correcting codes. And as Emina already said, this is joint work with Rawad Bitter, who's a postdoc in my group, and my PhD student, Andreas Lenz, and then also with Eitan Jacobi from the Technion. Okay, so let's start with the outline of the talk. So first I give the problem statement, which basically explains what are function correcting codes. Then we talk about irregular distance codes. So these are basically codes where the distance requirements between any pair of code words might be different. So usually we have in a code that any two code words should be at least distance d apart from each other. And here now we might have different requirements between pairs of code words. Then we'll talk about the optimal redundancy of function correcting codes and also how to apply function correcting codes then to specific functions. We'll see that all later. And finally, I'll give an overview and a conclusion. Now let's start with the problem statement. So assume Alice has a binary message u, and there's a publicly known function f, which we can apply on u, and then we can calculate f of u. So we later see examples for possible functions. For example, f could just be the Hamming weight of the vector u. Then u should be encoded in a systematic way. There are some motivations for why we use systematic encoding. Basically, we can see it as a storage setting where we don't want to alter the data itself. So it should be there and one should be able to read it without any modifications. And therefore, we just want to add additional redundancy. So therefore, we basically have u and p of u. So p of u denotes the parity. Okay, let me use the mouse. Basically, we'll denote the parity, so the redundancy that's appended to u. Then we transmit this over a channel. So this will be a substitution channel. So it's a channel that can flip at most t bits. And then on the receiver side, we have the vector y, which consists of two parts, u prime and p prime. And then Bob should decode this y. And now Bob is not interested in reconstructing u, but Bob only wants to reconstruct f of u. So clearly, a standard error correcting code can be applied. So we could just use a standard error correcting code or a systematic error correcting code on u, because if you have u and if the function f is public, then clearly you can also deduce f of u. But the question is that we were asking, how can we reduce the required redundancy? So depending on the function f, how much can we reduce it compared to using a standard error correcting code? Now in terms of applications, so there's some motivation coming from coded computing. So where we can see that a master distributes computations to several servers, and the function of interest might be the function that the servers compute. There's some motivation coming from storage, from data storage, where we have some archival data storage, and a user is interested in a function of a large data set, but the data itself should not be changed. So for example, it's the number of people who got infected with some virus from a large data set or something like this. And also partly from machine learning, where we can say that a function of interest is, for example, in a neural network, not the coefficients themselves, but somehow a function of the coefficients, which might characterize the capability of classification of this neural network. But so these are high-level motivations. So we are really interested in a fundamental understanding of this function correcting codes from a coding theory perspective. So the question is here, standard error correcting codes are too powerful. How can we do better? And as I already said, we're only considering systematic encoding. On the one side, this is because of the practical motivation that we do not want to alter the data. On the other hand, that's also because the problem is not interesting if we consider non-systematic encoding, because in that case, if the whole mapping is non-injective, then we will see that the optimal scheme is basically a standard error correcting code on f of u. And therefore, we consider the systematic setting. So related work basically mostly deals with very application-specific error correcting codes for certain functions. So for example, there are some works on codes for optimizing the output of a machine learning algorithm. So here, basically, the machine learning algorithm can be seen as the function. There are some works that cope with computation errors. So how to, like you do a certain computation and what can you do to correct these errors? There's something on functional error correction in neural networks, and also, well, there's reliable distributed encoding and function correction as a source coding program. So all these works are somehow connected what we are doing, but they are very specifically tailored to these functions, while we really try to gain a general understanding and a general theory for function correcting codes. Okay, so now here I want to mention 3 papers more in detail of related work. So there's the first paper by Kabir, Sala, Van der Broek, and Dolacek, where they want to protect the machine learning algorithm from errors in the training data. Then the second one is by Wang, Siegel, and Zhang, where the goal is to preserve the classification capabilities of a neural network. And the third is by Ronnie Roth, where it's basically to protect faulty analog dot product engines, so you do errors in the computation. Okay, so now let's go over to the formal definition. And by the way, so please interrupt me anytime you wish. If I'm too fast or you want something to be explained more detailed, you have a question, please go ahead, really just interrupt me and speak. I cannot see the chat basically when I'm screen sharing, so you either have to speak or somebody else has to say that there's something in the chat.
I can monitor, so please feel free.
So I guess I have one question is so here you know f of u exactly before you design the code, right? It's not like f is from some class of functions that you'd like to be able to decode.
Yeah. So you design codes for this function, but so you will see we also have results in general.
Okay, I was just curious. Okay, thanks.
Okay, so this picture we already had. Now if we go to the notations, so we have some message u. So as I said, we are only considering binary messages, but well, probably it's easily to be extended to query alphabets as well. Then f denotes our function. And now if you evaluate this function, it maps to the image of f, and we call e the size of this image. So the number of possible function values basically. And of course, that's at most 2 power k because we just have 2 power k possible inputs. Then we were considering an adversarial t substitution channel. So at most t bit flips. Okay, so x is the input, y the output, and we say that the Hamming distance is at most t. Okay, so that's the same thing again, the notations. So now let's go over to function correcting code. So how do we define it? So we say that the systematic encoding from binary vector of length k to a binary vector of length k plus r, which is done by appending parity bit redundancy to u, p of u. So p of u depends on u. And then this is a function correcting code for the function f. So you're right, it's tailored to the function in that sense. If for all u1 and u2, where the function values are distinct, we have that the Hamming distance of their encodings is at least 2t plus 1. Now, compared to classical error correcting codes, we see that the distance is only important if the function values are distinct. So for 2 input vectors that have the same function values, we do not require anything on their distance. And this is basically also why we can save redundancy. And we will later even say that it frequently makes sense to choose the redundancy not depending on U, but only depending on f of U. I think this is kind of natural because we just want to have it, want that they are distinct. If the function values are distinct, so we can also choose the redundancy just based on the function value. So now K will denote the message length, T the maximum number of errors, and R the redundancy length. Okay, so this is again the definition. Then we denote by RFKT the smallest redundancy R, such that there exists an FCC for a certain function f. So it depends on the function, it depends on the input length, and of course it depends on the number of errors. Now, some remarks. So first of all, due to this distance constraint, that the distance between any two encodings where the function values are distinct is at least 2t plus 1, we can uniquely reconstruct f of u if the encoding of u and y are at most t having distance t apart. Now, if f is unknown to the transmitter, of course, you cannot do anything better than standard error correction. And therefore, we are assuming that f is known to the transmitter, such that we can encode in a good way. If f is bijective, then it basically results in a standard error correcting code because clearly all function values will be distinct. So we have this requirement in any pair of code words. So of course we end up with a standard error correcting code. If f is
Antonia, sorry. So when you evaluate the function, you first read the data, say it's recorded somewhere, and then decode it, and then you evaluate. Is that how you?
You mean if you're encoding here?
Right.
So yeah, you read the data and somehow calculate a function of the data.
Right.
But it not necessarily. I mean, this we haven't talked about this yet, how this encoding is done, right? Of course, we will later see that it does make sense to do it as you suggested. So we have reading the data, calculate f of u, and then use this as input to the systematic encoder. This makes sense in many cases, but it's not necessarily like this. So here in this picture, you basically just read the data and do something in this encoder to calculate p of u.
I see. All right. Thank you.
This might include calculating f of u, but not necessarily.
Yeah, I was trying to understand the reason for having a distance between the images.
Yeah, because otherwise you wouldn't be able to reconstruct f of u, basically.
Okay.
It's yeah, you really need the distance to be able to do unique reconstruction.
Okay.
Sorry, then so the decoder has to download all of gets. I guess I was fixated on your there's a big legacy data set around, and you'd like to only learn some function of that data set. But there, you still have to download. The decoder still has to download something that's the same size as the data set, right?
You mean here?
That is, yeah. You have to decode. Yeah, the decoder has to get y, which is u prime is as big as u. So like, if,
yeah, exactly.
So 1 terabyte data set, you're going to have a 1 terabyte file that you downloaded anyway. Okay.
Yeah, plus some.
But it might be corrupted. So you can store it in the clear. Essentially, you can store it in the clear on the server and then still be able to recover the function. Yeah.
Yeah, you can.
Okay.
Okay, so the last observation also, like if f is constant, then clearly we don't need any redundancy because it anyways gives the same value always, so we don't need anything, and it's known to everyone, so we don't need any redundancy. Okay, so now this is like in general our contribution. So we'll first build a general theory for general functions and adversarial channels, and then also we directly see a connection to irregular distance code and lower and upper bounds on the redundancy. Then we'll apply it to specific functions. Yeah, we'll see that later in the talk, so I don't want to say too much about it. And independently of these function correcting codes, or actually because we are investigating irregular distance codes, we are also giving bounds on irregular distance codes, which is something that's not hasn't been investigated much in literature. Also because it quickly becomes complicated, I have to admit. But still, so we have derived a Plotkin and a Gilbert-Wassermann type bounds on irregular distance codes. Okay, so let's first talk about irregular distance codes, and later we will see the connection to function correcting codes. So what are irregular distance codes? So first of all, so assume we have a so-called distance matrix of size m by m. Okay, so it's just a symmetric matrix with zeros on the diagonal, and all the non-zero or all entries are at least 0. And then we say an irregular distance code is a set of words of size m, and with this distance requirement matrix, if the distance between pi, pj is at least dij for all I and j in the set. So this matrix basically tells us the distances between the different code words. Of course, if we have an all zero diagonal and all other entries are equal, then we have a standard error correcting code. And now we denote by this NMD. So that should be the optimal length. So it's the smallest integer such that there exists an irregular distance code of cardinality m and this distance requirement matrix of length r. Now we basically want to find bounds on this optimal length, because it will later also give us bounds on function correcting codes. So we'll actually see that we can get a lower bound on the redundancy of function correcting codes by having a lower bound on the length of irregular distance codes. And therefore, we have derived a generalized Plotkin bound. And basically, yeah, so basically that's the statement, which means that this optimal length is lower bounded by these values, depending on whether m is even or m is odd. So we can have a look at the proof. So first of all, I want to mention that it reduces to the standard Plotkin bound if all the entries of dij are d, then it's exactly 2dm minus 1 divided by m. And actually a proof that we are doing here is also quite similar to the classical Plotkin bound. So here the idea is shown for m even. So we write the m code words that have length r into the rows of a matrix P. And then if we want to calculate the sum, so the sum over the distances between two different rows, then we can look at each column separately. Now, if a column has weight exactly m half, then it will contribute exactly m squared over 4 to this sum. In other cases, it will contribute less. And then you can just, if you go over all columns, then you will basically get this. And then by definition, since this has to be at least the distance, we get this statement here. So this is quite similar to how the standard Plotkin bound is proven. And the odd thing is the same, it's just then since it's not divisible, you get this factor -1. Okay, so we also looked at a generalized Gilbert-Wassermann bound for irregular distance codes. So this is, so as the standard Gilbert-Wassermann, this is an existent bound on the cardinality, so an achievability bound. So it basically says that the smallest length of an irregular distance code of size m and with this distance requirement matrix is upper bounded by this function here. So this phi just says that the statement holds for any selection of the code words in the proof. So we'll see this. Now this V, this denotes a Hamming sphere of this radius and for words of this length. And now also this generalizes the classical Gilbert-Wassermann bound. So if all the entries of the distance requirement matrix are equal, then we get the classical Gilbert-Wassermann bound. Now for the proof, so we construct such a code of length r, which meets these distance requirements by iteratively selecting valid code words. So first of all, we choose code word P1 arbitrarily. And then, of course, we have to choose P2 such that the distance is at least D12. Now, of course, this exists if P2 lies outside the ball of radius D1, 2, minus 1 around P1. So it exists if this ball is smaller than the whole space. And then we iteratively continue. So then we choose P3 such that this holds between P1 and P3 and between P2 and P3. And then we say it exists for sure if the whole space is still larger than the sum of those two balls, and so on. And then the statement follows by iteratively selecting code words. And yeah, so we first of all, we see that if all the DIs are the same, then we get a standard Gilbert-Wassermann bound. We can also see that this is maybe a bit too much, so we can do better probably. It's possible to improve this bound by allowing some overlaps, and also by cleverly choosing the iterative selection of the code words. But yeah, so this is a Gilbert-Wassermann bound on irregular distance codes. But now, why were we actually considering this? Our motivation was to have a relation to function correcting codes. So let's try to understand what we are doing here, or why this is why there is a connection. So first of all, we define the distance requirement matrix for a function f. So assume we have these information vectors given, then we define this distance requirement matrix like this. So we have 0 if the function values are the same, because basically we don't care. Now, if the function values are distinct, then we say that the entry at this matrix is 2t plus 1 minus the Hamming distance of the two information words. So this basically corresponds to a function correcting code, because now we can see so we construct an irregular distance code with this distance requirement matrix, then append this as redundancy to our information. Now the two information parts already have distance du, I, uj, and then their corresponding redundancies have distance 2t plus 1 minus du, I, uj, so the total word will have distance 2t plus 1. Then we see that this is basically what we want from a function correcting code, that if the function values are distinct, we have distance at least 2t plus 1. And that's basically what it says here. So the minimum redundancy of a function correcting code is exactly the smallest length of an irregular distance code of size 2 power k, because that's the number of possible messages that we have with this distance requirement matrix. Yeah, and the proof from this is basically the first part follows from the definition of a function correcting code, and the upper bound basically, as I just said, so we use the code words of the irregular distance code as redundancy of the FCC. And then since the corresponding information words already have this distance, which then the Hamming distance adds up. So in total, it has distance 2t plus 1. Now we can also simplify these bounds, because in general, so here we see that that this holds if we really have size 2 power k, and we use all possible message vectors as input. And so this might hard to find such codes. So we can actually simplify the problem a bit by not using all possible information vectors, but just a subset. So if we just use a subset of information vectors, it might be easier to determine nm, so the length of the irregular distance code. So this now acts only on a subset of information vectors, and it still gives a lower bound. It's easier to analyze, but it's possibly not tight. That's why we also only have a lower bound. And so yeah, it's also quite challenging to find a good subset of information vectors that will provide us a good lower bound. So for some choices, we might even get a tight lower bound, for others not. So this is not easy to say. In general, it seems to be good by intuition to have that we get good bounds for information vectors that are close in Hamming distance, but have distinct function values. Because this is, of course, the most challenging task. So the information words don't have a large distance. Therefore, if we look at this part, the irregular distance code has to have a larger distance between those two for those two message vectors because DUI/UJ is not as big. So this seems to be the most challenging task, and then you get tighter bounds if you use such message vectors for determining NMDF. Okay, so now we can actually further simplify it and show the existence of function correcting codes of small distance. So first of all, we define something called the function distance, which now depends on the function values explicitly. So the function distance between F1 and F2, between the function values, is the minimum Hamming distance between U1 and U2, such that U1 has function value F1 and U2 has function value F2. Then we can also give a function distance matrix here. So this looks quite similar to what we had before, now just with the difference that it really depends only on the function values. And we see that now we basically required all entries because the FIs are all distinct, except for the diagonal, of course. And so frequently this is easier to derive than the distance requirement matrix because it only depends on the function values and not on the UIs. And then we can prove that the minimum redundancy of an FCC is upper bounded by the smallest length of an irregular distance code of size E. So this is also the size of the image of the function and this function distance matrix. Now here we really then, the proof of this basically does what I mentioned a few times before. We choose the redundancy that it depends really only on the function value. So P of U just depends on F of U, P depends on F of U, and we can just denote PI by P F of U equals Fi. And then we choose the PIs such that the distance is at least 2t plus 1 minus this function value. And then basically since the function, if the function values have this function distance, then it implies, of course, that the distance between the message vectors is already this value. So, and therefore, in total, we will always have the 2t distance 2t plus 1. So the whole idea here is that if we use an irregular distance code that depends on the function values and use this as the redundancy, then we get this bound. So assigning the same redundancy to all information vectors that evaluate to the same function value definitely makes sense. Okay, so now this maybe became a bit technical. Now let's go over to applying this to specific examples. So we start with locally binary functions, which we define as follows. So first of all, we need the function ball of radius rho. So this function ball basically gives a set of all function values that I can reach from U with all information vectors of distance at most rho. Okay, and now if the size of this function ball is at most 2, then we call this a rho locally binary function F. So just to illustrate it, so this is a locally binary function because if I draw the function ball like this, it will just contain at most, so here it will contain 2 function values, here it might contain just 1, here 2. So if rho is small enough, then this is a locally binary function. Whereas here we can easily draw also for small radius a function ball that contains 3 function values, so a function ball of size 3. Now we can sort of talk about examples of locally binary functions because somehow that might not be a well-known definition. So one example is the codeword indicator function. So assume this Q is a standard error correcting code with a minimum distance D. And this indicator function, if we use it on a vector U, it will return I if U is codeword QI and 0 otherwise. Now I claim that this is d minus 1/2 locally binary, and that's basically the case because if you draw a function ball of radius d minus 1/2, then you're basically considering at most one code word, and all others are not code words. So you have probably just have I and 0 in this function ball, so it always has size at most 2. In some cases, you might only have 0 in the ball, and then therefore it's locally binary if rho is this radius.
Should I interpret this as saying, you know, the actual data U is itself already encoded, and this is just a decoder? This code word indicator function is a decoder for you. Is a decoder for you. Because it'll output the message corresponding to because you're assuming that the source data U is already encoded with an error correcting code.
Yes, let me surely think. Is this really true?
So like I would have an underlying message that I encoded into U, which I store in my hard drive or whatever as an error correcting code as a code word.
Yeah, I think you can see it like this. Yeah.
Okay, that's true. Cool.
Another example is this Hemingway distribution function. I'll also mention that more detailed later. Here, the idea is basically it's a step function, which is input uses the weight of U, and the output is what you see on the y-axis here. And now you see that if you make a function ball radius at most 2t, and if this step width is 4t plus 1, so this radius is at most half your step size, basically, then you can see you can just cover basically 2 function values, because you can just go from here, you can go up to here and then up to here, so you can just cover 2 function values. So it's also a 2t locally binary function. And now for such 2t locally binary functions, we can prove optimality. Because we can actually state that the required redundancy is exactly 2t. We also have an explicit coding scheme for this, which basically relies on just using replication. I don't want to go into detail about the proof, but the nice thing that this is really an optimal scheme. So now we can look at other examples of functions. So for example, just the Hemingway. So clearly, so in the Hemingway, we have that the function of U is the weight of U. So it can have k values because it's a length k vector. So Hemingway can be between 0 to k. And then our function distance matrix can be defined like this. So clearly diagonal is 0. And on all the other entries, we have 2t plus 1 minus the absolute value of I minus j, because if we have if one word has weight I and the other one has weight j, then their distance also has Hamming weight at least I minus j absolute value. And therefore, we only need to add 2t plus 1 minus I minus j to the distance. And then also, therefore, the function distance matrix looks very systematic. So yeah, so if we have a weight 0 word and a weight 1 word, and if we want to have that their total distance is 5 because t is 2, so we want to have 2t plus 1, then so this weight 1 and weight 0 word, they just have distance 1 right now, the information part. So we need to add a further distance of 4 in the redundancy part. Whereas, of course, a weight 0 word and a weight 5 word, they already have distance 5, so we don't need any distance in the redundancy part.
So Antonia, I have a quick question. So what I understood from the beginning is that the function is one-to-one or injective, you mentioned. Is it because here, does this still apply for the weight function?
Did I say this? I didn't mean
or maybe I misunderstood it, because you said that the function, the code is systematic, right? So yes. Should you, I mean, in my mind here, you should send less than the code, than the information to be able to send the weight, to decode the weight.
Should send less than the information.
Yeah.
Yes, but that's the, yeah, okay, so now I get the question. So yeah, if you don't require, let's maybe go back to the
it seems to me it's wasteful to have a system like you see what I'm
Yeah, you're right. So if you don't have the systematic requirement,
Yeah.
then you could just use an error correcting code on f of u. That's basically what you're suggesting, right?
Yeah.
To not have a systematic encoder, but do an error correcting code on f of u.
Yes.
Yes, but then the whole problem becomes not interesting, because then it's already solved. You get the best you can do.
So how do you enforce this setting? Maybe you mentioned this at the beginning, I missed it. So how do you enforce in the setting that you have to send this?
Well, that's of course it's a bit first of all, so mainly we are interested in this because then it makes the problem mathematically interesting, to be honest. But also you can see it like from a practical point of view, you can see it like you have a storage system, you have some data that should be there without being changed, right? So you have a large data set and you don't want to change the data itself, but just store something additional, because maybe somebody else still wants to access the data in its original way.
Maybe this is what Anand was also asking about, I don't know, or someone else. Okay, thank you.
Yeah, that was my question. That was my question, I guess. So I guess maybe Salim, your point is also that and it was also, I guess, my other question was like that the decoder has to get U prime. It can't just operate.
Yeah. So
yeah, exactly. So that's yeah. We just have the requirement. The decoder also somehow needs the data itself. Exactly.
Okay, thanks.
Okay. But yeah, it's good if you are asking this, because that is an important thing to ask, actually. Where were we? So we were the Hamming weight. Yeah. So then we get this very regular matrix, actually. We can see that we achieve the optimal redundancy even by assigning redundancy vectors just based on function values, so as we said before, and we can give code constructions. So we see for t equals 1, we have this p of u, which basically just depends on the weight of u, and it also it cyclically rotates through these 3 vectors. So we see that so u0 and u3, for example. So here those 2 already have Hamming distance 3, so their redundancies don't need to have any additional distance. Whereas if we have weight 0 and weight 1, we only have distance 1, so we still need to add distance 2. And this is actually even an optimal construction for t equals 1. And we can do a similar thing for t equals 2. But this we can generalize this, but then it's unfortunately not optimal anymore for general t. For general t, we only get basically the 4t as redundancy and asymptotically 10 divided by 3t from our Plotkin type bound as a lower bound. If we compare this now on having, so we'll have a comparison table later also, but just mentioned already, if you compare this on using just standard error correcting codes, then the redundancy is approximately t log k. So we are basically getting rid of this log k at the expense of having some constant factor here. Now we also looked at the Hamming weight distribution function, which is this step function that I mentioned before. So it's basically just the weight of u divided by t. And so this is the function that we get then. Now, if t is at least 4t plus 1, I already mentioned it, then it's a 2 locally binary function. And we get this optimal redundancy. Now we can also show an explicit construction for this, which basically can do the following. So we can assign, so if we look at the weight here, so we assign to this, to weight 0, we assign the redundancy vector, the all 0 vector. To weight 1, we assign 1 and then all zeros, and then 1, 1, 0, and so on. So we just go through it lexicographically, whereas this is then the all 1 vector of weight of length 2t all. And here it's again the all 0 vector. So we don't care about the distance between any of these 2 information vectors, or also not redundancy vectors, because they have the same function value. So we just have to take care that if we have one word from here and one word from here, the distance is large enough. Now, if we have all 1 here and all 0 here, then the redundancy have distance exactly 2t plus 1 from the information distance, and so on. Those two still have distance 2t minus 1, and so on. So we can guarantee that the distance requirement is fulfilled. Now we also looked at the min-max function, which is an ordering function. So assume that we can split U into W blocks, but the blocks all have length L. And now this f of U is this min-max function, which basically orders primarily lexicographically. And secondly, if Ui and Uj are equal, then it will just order by index. So if we look at this example, so if this is our vector U and these are the blocks, so then we see that so U2 is smaller than U3. That's because of the index, because the index of 2 is smaller, although they are the same. And both of them are smaller than this one, because lexicographically 0, 1, 0 is smaller than 1, 0, 0. So we get this ordering. And then the min-max function will just output the index of the smallest and the index of the largest. So it will be 2, 1. So in this example for t equals 2, we then get this distance requirement matrix, and we see that this is very regular. So we basically always have 2t in each entry, which shows us that in this case, also using a standard error correcting code will actually give quite a good result. In general, by our plotkin type arguments, we get this lower bound, and we can show some construction using read-Muller codes, which is basically just 3 bits away from this lower bound. Okay, so finally, we also looked at quantized real-valued functions, so a bit with the motivation of machine learning. So these are basically functions that can be seen as loss functions, for example, in gradient descent, but of course they are also used in many other applications. So first of all, we looked at the sigmoid function and its derivative, and then tangent superbolicus and the derivative, and also the rectified linear unit function. So, but we do not, so those functions are of the form that they map real values to real values. But what we are doing in our function correcting code setting, we consider digital functions, so that map a binary length k vector to a function value. So we basically use quantization intervals here, and we use the quantization center to represent this interval. So that's why quantized real valued functions. As an example here, the sigmoid function, which looks like this. We can assume that it's constant for large and small values. So we can basically just assume that for at least 10 it's constant, and below -10 it's also constant. And then on the rest, on the remaining interval, it's bijective. This is our assumption. And then we represent the values in this interval from -10 to 10 by a 5-bit vector with quantization centers -9.5, -8.5 up to 9.5, so with distance 1. So we basically map each vector in this interval -10 to 10 to one of these quantization centers, to the closest one, basically. So we split it into intervals and map it to the centers. And then we can say that this function, this quantized function of U, okay, I called it machine learning sigma of U, but this is just a name, should be 0 for representing the value, all values smaller than -10. And it should be 1 for all values representing something larger than 10. And it should be the sigmoid function of these quantization centers for anything in between. And then you can build a function correcting code by using a 22 by 22 function distance matrix d sigma. And basically, this is quite similar to what we did before. So we require for each entry, we require 2t plus 1 minus the distance of ui, uj, where this is really, this depends on the mapping, how we map these 5-bit vectors to these quantization centers. And then we can build a function correcting code with this redundancy. So this is again the smallest length of an irregular distance code. of size 22, sorry, and this distance requirement matrix. And we see that here, yeah, so for all values below -10, we just have a single entry here, and for all above 10, we also just have a single entry here. Okay, so in general, we can also generalize these statements. So in general, if this epsilon denotes our quantization interval width, and this b minus a divided by epsilon is the number of quantization intervals that we have, and then in general, we can say that the redundancy that we require is given by an irregular distance code of size number of intervals plus 2, and this distance requirement matrix if our function satisfies to be equal to 0 for all x smaller than a and 1 for all x larger than b. So this basically just generalizes the sigmoid function that we were just looking at. It also works for the tangent hyperbolicus. Now, if we, for example, look at their derivatives of the sigmoid and the tangent hyperbolicus, then we can save 1 in the cardinality. That's clear because basically, if we look at the matrix, so here we have 0 for the left part and 1 for the right part. Now, if we have, let me go back, for example, the derivative, then we can represent both the left and right part by 1 function value. So we basically save 1 row and column in this matrix. So we wouldn't have the last row and the last column. And then we just get number of intervals plus 1 and this distance requirement matrix. Okay, so now finally, let's compare the redundancies to if we use some standard error correcting codes. Okay, so what do we see here? These are the functions that we've considered. These are some parameters. So like, for example, this threshold for the Hamming weight distribution function has to be at least 2t plus 1. This lower bound is basically what we have calculated, what we have seen before, the 2t or the 10 divided by 3 times t. Now the ECC on data, that's basically if we use a systematic encoding on U. So it's basically a standard error correcting code that takes U as the input, input message length k, t errors, so distance should be 2t plus 1, and then by just using an alternate code, we require asymptotically redundancy t log k for all cases. Now ECC on function values, this is basically something similar to what Salim was also asking about, but still, since we are still in the systematic setting, that would mean, in this case, we use an error correcting code on f of u, which can also be non-systematic, but then append this error correcting code as redundancy to u. And then our redundancy is basically length of this error correcting code that encodes f of u. And also assuming that we use an alternate code there, then we get this log e plus t log e for most of the cases. Well, this is basically, these are our results that we got from our constructions. So we see that the nice thing is that it only depends on t and it doesn't depend on k as basically in these cases. Okay, so this already brings me to the end of my talk. So we have introduced function correcting codes over adversarial channels, so at most t errors. I should add the systematic here. So we really have the setting that that our data should be stored as is, that it shouldn't be changed. So we have the systematic requirement. We've shown the relationship to irregular distance codes, namely that, yeah, that basically the redundancy of an FCC is equal to the size of an irregular distance code, to the length of an irregular distance code, not the size. And we have shown close to optimal redundancy or even optimal redundancy for some examples. Open problems are more general constructions for irregular distance codes. That's challenging because if our cardinality is large, then we have so many requirements between different codewords. That's gets quite quickly a hard problem. And of course, we want to close the gaps between lower and upper bounds and investigate other functions. Okay, thanks a lot. And I'm happy to have more questions.
Thank you very much, Antonia.